Good morning, all. In our last lecture, we discussed about different indexing structures. We have discussed primary index, secondary index, as well as clustering index and multi-level index too. When if you have an indexing structure, and let B is the number of blocks in the indexing structure, then you can perform a binary search by log 2 to the log B to the base 2. And if we have a multi-level index, the search time can be further reduced. For example, in our previous lecture, we have seen that with a multi-level index, the number of block access is reduced from 10 to 4 because there were only three index levels in the multi-level index that we created, and 3 plus 1 4 block access instead of 10 block access in our previous example. And today, and we know that a multi-level index with R1 first level entries will approximately have t is equal to log R1 to the base f4 upper limit levels. This is the number of levels in a multi level index structure. What is f4 means? F4 is fan out. In our previous example, there were 68 entries per block. That is why it was fan out was 68 entries to the number of blocks required, that is 3000 or something, the number of blocks required. That is how we got the number of levels as 3. Still faced with problems, even though this multi-level index is good, but there are some problems like insertions and deletions because all index levels are physically ordered. Once it is physically ordered, you cannot add more than a certain limit until the limit the capacity of that block structure. More than that you cannot add. Thus designers adopted a multi-level index that leaves some space in each of its block for inserting new entries. Therefore, what is required is a multi-level index, but with a dynamically varying adding capacity. That is what required. It's called a dynamic multi-level index is required. Before going to and we will be discussing first search trees. Before going to the exact B plus tree or B tree, first we will discuss search trees as a general. Search tree of order P is a tree that each node contains at the most p minus 1 search values and p pointers in the order p1 k1 p2 k2 up to pq minus 1 kq minus 1 and pq. Here p1 p2 up to pq are pointers, and k1 k2 up to kq minus 1 are q minus 1 number of search values or search keys. For all values of x in the subtree pointed by pi, we have ki minus 1 less than x less than ki for I 1 less than I less than q. For example, this is what it is expressed in this statement. That is for a search value x which is less than ki minus 1 and which is greater than ki minus 1 and less than ki, then we have to take a path this pointed by this pointer. For this pointer is pi. Or if the search value that is less than the k1 key 1 or the first key value, then you have to take a path pointed by p1. Therefore, this p1 is pointing to a subtree. Each of the pointer is pointing to a subtree with the same node structure, and based on the search value you can branch appropriately. Therefore, in the case of binary tree you can have only two branches. Here it is a in this multi-way search tree, what is required is a better algorithm is required to guarantee that such a tree is always balanced. Okay, consider an example of a multi-way search tree having nodes like structure like this, and let us assume we want to search whether 11 is present or not. 11 is present means the lookup is like this: search in the root. Here it is root having a key value 5. 11 is greater than that, therefore we will move to this branch, and here 6 and 9 they are the key values. It is again greater than 9, that is they will go for this one. Here there is no 11. That is why it is the key is not found. If it was solved, you can find out of that. This is how a tree search. And here the issue here is, if the tree is left aligned, or left tree, or a right tree alone, if the single node with children are going like this, or like in this direction only, then it is a it become difficult to search for a given value, because it will take it will be similar to a linear search. For the tree structure, the structure of tree is important. It must be a balanced one. Therefore, that is why a dynamic multi-level index using B tree or B plus tree, it is balanced trees. Here it guarantees that the tree is always balanced. Tree created or the tree constructed from the list of key values is always balanced. Most multi-level index use B tree or B plus tree data structure because of insertion of deletion problem of multi-level index. This leaves space in each tree node to allow for new index entries, because in the case of multi-level index, the issue is a fixed structure. Now you can add any number of nodes, or it can be dynamically increased. B tree has additional constraint that ensures that tree is always balanced. Therefore, a dynamic multi-level tree, or B tree or B plus tree, solves both problems. In the case of multi-level index, you have the problem of limiting the number of entries possible because of the fixed structure, and also a ordinary search tree, a multi-way search tree, can grow in either direction, or a left or right tree it can become a left tree or right tree, and again the problem of search become inefficient. That both issues are solved, because dynamically this tree can increase the nodes, and as well as it is always balanced, and space wastage by deletion, if any, never become excessive. Therefore, all these issues are solved in B tree and B plus trees. And the structure of a B tree. The structure contains similar to a multiverse. It's a multiverse search tree. Here the structure is P1 up to PQ tree pointers, and K1 up to KQ minus 1 data or key values. But the key values is a pair. Pair means key value associated with a data pointer. K1 PR1. PR1 is data pointer. What is a data pointer means? This points to the block containing the record, which is key for the key K1. K2, this P2 means the tree pointer. P1, P2, PQ are tree pointers. That is, whenever you search for a value x which is less than ki minus 1 less than x less than ki, that is between ki minus 1 and ki, we will take this path, and again the search will be recursively done. But whenever you search for a data value that is present directly, this k value, let be k1 is the search value, that is you directly got k1, then the exact record where it contained is pointed by pr1, that is this is pr1 is a data pointer. Therefore, this pr1, the leaf node or the root node or intermediate node, any of the node can have this key value associated with the data pointer. This is not the case of B plus tree. In the case of B tree, this is a structure. The structure is same for root node, intermediate node, as well as leaf node. This is an example of a B tree having the same structure with some set of values. Here, this is a tree pointer. This is a tree pointer. This is another tree pointer. What is shown in this dot is PR, the data pointer. If the search key value is 5, then you can directly go. If it is 8, directly go to that one. Otherwise, this is way. And you can see that the leaf structure is also the same, but only the difference is that in the case of leaf structure, the tree pointers are assigned with the null values. The structure is the same, but tree pointers are assigned with null values. And this is the structure of a B tree. A showing a node with B tree with q minus 1 search values, and B a B tree with p is equal to 3. Since p is equal to 3 means you can have 3 tree pointers and 2 key values maximum. And there are some constraints on the what is the minimum number of key values and minimum number of tree pointers from each node. Such constraints are also there in B tree. And okay, B tree. A B tree of order P can be defined as follows. Each internal node in the B tree is of the form P1 K1 PR1, P2 K2 PR2 up to K Q minus 1 PRQ minus 1 PQ. That means you must the tree in a node can have P1 up P2 up to PQ number of tree pointers and Q minus 1 number of key values. Key value means key value data pointer pair. And within each node K1 less than K2 less than K3 etc. That means all the key values must be in increasing order. For all search key field values x in the subtree pointed at Pi, it must satisfy these conditions. That is Ki minus 1 less than x less than Ki for I is equal for 1 less than I less than Q. That is for this diagram. This is what it is shown. This is the case, that is 1 less than I less than Q, Ki minus 1 less than x less than K. For the extreme cases also the condition is specifically mentioned in point 3. Each node has at most P tree pointers. The maximum number of tree pointers is P only, each node. Each node, what is the minimum number of tree pointers? The minimum number of P pointers is P by 2. P by 2 upper seal means the upper. If it is 3 1 by 1.5 then it should be 2 odd. A node with Q tree pointers where Q is less than P has Q minus 1 search key. That is this is how the tree is always become balanced tree. Each node must have P by 2 tree pointers and Q minus 1 search key values. All the leaf nodes are at the same level. Leaf nodes have the same structure as internal node except that all their tree pointers are null. The leaf node as well as intermediate node as well as root node are having the same structure in the case of B tree, but it is different in the case of B plus tree. But the only difference is that in the case of B tree, the leaf nodes there is no tree pointer or tree pointers are null values. Are having null values. This is an example of a B tree with 8, 5, 1, 7, 3, 12, 9, 6. These values inserted. And the structure that you got is like this. This is a root node. This is a leaf node. What is shown in red is a tree pointer. What is shown in blue is a data pointer. This is a null pointer. In this leaf nodes, this is this as well as this and null pointers, and these are tree pointers. These are the values. How these values are arranged we will see, and with an example in the case of B plus tree. Actually it will start filling up in the leaf nodes. Then if it is if there is no sufficient space, then it will build up and up, and like that tree can begin. A tree start with a single node at level 0. Once a root node is filled up with P minus 1 search key values, and when we try to add a new key, the root node is split into 2 nodes at level 1. Only the middle value is kept in the root node and the rest of values split evenly between the other 2 nodes. That is the idea here. Whenever there is whenever a node is full, for the space to occupy another element, another key value, that is split into 2, and the middle value is in the level is put in the level 1. The leaf level there will be 2 nodes. That is the case of root node. When a non-root node is full, the new entry is inserted into it. When a new entry is inserted in it, the node is split into 2 at the same level, and middle entry is moved to the parent node. This is how a tree is built. Exactly we will see in next class. Therefore, this is how the structure of a B plus B tree. Here in the root node we have tree pointer as well as data pointer. This is a data pointer. This is in the case of key value 5. This is the data pointer. Okay, and lookup here is, for example, we want to search for 7. Then starting with the node 5 in the root node, it will perform a linear search, and 5 next key data value is 8. Therefore we will take this path, and the search value 6 and 7 search value can be identified from this node. That is how the lookup will be performed. B tree, by deletion of a value causes a node to be half full. It is combined with its neighboring node. Same as like the insertion. Whenever a new value is inserted into a node, if there is no space, then split will be taken place. And in the same case, when a key value is deleted, and then this half full, it become half full, then two nodes are combined together, and this propagate all the way to root during the deletion. It has been shown by analysis and simulation that after several insertion and deletion on B tree, the nodes are approximately 69% full when the number of values in the tree stabilizes. This is an analysis, and by simulation it has been shown that after several insertion and deletion, in the case of a B tree, it is 69% full. Suppose that the search field is 9 bytes long and disk block is 5 bytes. A record data pointer PR is 7 bytes and block pointer P is 6 bytes. Now what is question here is, given a block of 512 bytes and search key field values data bytes is 9 bytes, disk block data record data point size is 7 bytes, block pointer size is 6 bytes, then how many entries is possible in a block of 512 bytes? The number of entries possible in a block of 512 bytes if these are the length of or the size of each of the field. Now how many tree pointers you can have? Let be p number of tree pointers and p minus 1 number of data as well as data pointers. Therefore what is the inequality you can write? You can write like this: p into p is the number of tree pointers, p into p. What is a p? What is capital P indicates the size of tree pointer, plus p minus 1 into pr is the size of data pointer, and v is the size of data key field. Key field require 9 bytes, data pointer requires 7 bytes. So 9 plus 7, 16 bytes. 16 bytes into p minus 1 entries, and p into the data point block point 6 byte, p into 6, p into 6 plus p minus 1 into 16 less than 512. You will get a value for p. That value is 22p less than 528, less than or equal to 528. When you divide, you will get 24, but there is some more space required. Therefore what you can do is, you can take if it is 23.5, then it's okay, 23. If it is exactly division, then you take a value which is 1 less than the actually division. Here in this case 20 p 512 divided by 20 is exactly 24. Therefore you cannot fit exactly like this. Some more additional field needs to be stored. That is why we took 23. P is large value, that satisfies the above inequality. This is how therefore what is the meaning of this? Here this meaning is, in a single in a disk block, a node structure, if we fit a node structure, then the number of entries or the number of tree pointers there is 23 if the size are as given above. And one more point, assume that we have constructed a B tree with the specification mentioned in the previous example. On an average B tree is 69% full. Then each node will have 0.69 into 23, that is 16 pointers, and hence 15 keys. Our assumption is that again 69% full. Previous case, what was the p value you got? Just 23. 23 into 0.69 is 16 pointers. That means your nodes are having 16 pointers, and that means 15 key values. Given the block size, pointer size, search key field size, and average number of entries in the node, two-level block tree will be having 3840 plus 240 plus 15 4095 entries. We'll check how it comes. Because in the root level is root, number of node is 1, number of key values 15, and number of pointers 16 tree pointers and 15 key values, only one root, one node. In the level 1, how many nodes? Because there are 16 pointers, there will be 16 nodes in the level 1. That means 16 into 15 is the number of key values in a node. 15 into 16, 240 key values will be there in level 1. And number of pointers there are 16 nodes. Each node can have 16 pointers. Therefore, 16 into 16, 256 is the number of pointers there. Now, level 2, there are 256 number of nodes. 256 into 15 is 3840, and 256 into 16 is 4096. Therefore, if you sum of the number of entries, it is, if a tree with level 2 levels is 3840 entries in the level 2, 240 entries in the level 1, and 15 entries, this is the number of entries. Number of nodes with the level 2 is 1 plus 16 plus 256. Okay, this is what the structure of a B tree. In next class, we will be looking into how B plus tree is constructed, or what is the peculiarities of B plus tree. Thank you.